Okay, guys, I'm going to try to use some of the terms from Chapter 4, Section 3 and explain something that's not in your book that is really important to understanding all this. So let's talk here a little bit first about the most important trend to understand in the periodic table, because it explains so many other ones, and that is the trend of atomic radius. That's like ionic radius in that it's the size. But if you're talking about the size of a neutral atom, like the regular number of electrons in it, then you're talking about atomic radius. If it's gained or lost and formed the ion that it likes to form, then of course it may have a slightly different size because it's got a different number of electrons in it, and that's called ionic radius. We'll spend most of our time here talking about atomic radius and what causes it. So let me show you something real quick up here. There is a physics topic that you probably will not find. You probably will not find it in a chemistry textbook very often. It is called Coulomb's law. He was a Frenchman, and if you are at all familiar, with Isaac Newton's law of gravity, it's a similar kind of a thing. Newton knew that the moon was going around the Earth. We now, talk about the orbit. It's kind of elliptical. It's not exactly circular. He came to understand that if the moon was changing its direction to orbit the Earth, there had to be a force causing that. And he hypothesized that the same force that was causing that was what was causing, like the apple to hit the ground or whatever. He hypothesized that they were the same force. And as time went by, we made some measurements and figured out that the more mass that you have and the closer you are, the greater that attraction is. All right, had a slight interruption there. But anyway, Newton's law dealt with gravity. Coulomb's is about like this. If you want to know what it really finds is the force between charges. Now this could be like a plus and a plus, but we kind of know that those two are going to repel away from each other. It could also, be between two minuses. Of course, a plus and a minus is going to be an attractive force, and that's the one we're most concerned with, because this is the way protons and electrons are. One of them's positive, one of them's negative. So here's what he sort of found mathematically, that the force of electrical attraction depends upon a constant K. As you know, we often have laws that have constants in them. There is Q1 and Q2. The Q1 and the Q2 are the two charges. So like one of them will be so much charge and then be multiplied by the other one. So what you see is that, and this kind of makes sense, if you have two socks and they stick together a lot, it's because they both have a lot of static charge built up on them. And so that is one of the factors. The other one is the distance, and it's not just a lineal distance, it's actually distance squared. Now, if I were to write Newton's law of gravity, which I guess I could put up here real quick for you, you would notice some striking similarities in the form of the equation. Let me jot it up here just for reference. The force of gravitation is big G, which is a universal gravitation constant. It's like playing the role K here, times mass 1 times mass 2 all over d squared. So gravity and electrical forces both have very, very similar forms. And Coulomb is the one that you don't hear about as much, but he figured out the electrical one. Okay, so let's get to what this means for us in all this. I'm going to draw a couple of Bohr models, and I want you to think just a little bit about how this would play into these Bohr models. Bohr models, as you know, are outdated, but they're useful for some things. So let me just show you a couple real quick. Let's take, for example, let's take nitrogen. Nitrogen is atomic number 7. So there would be 7 protons in the nucleus, and it weighs 14 in its most common thing, so there would be 7 neutrons also in the nucleus of that atom in like the most common isotope. The electron shells, as you know, there's like a 1s, 2s, and all that. But the first shell basically holds 2. That would be like your 1s2. So 2 negative charges there. And then your second shell, which I'll just sketch on there, if you look, it would have to have 7 altogether, and so it is S2P3, but it's just 5 in the outer shell. Now here's what I want to get at. This is nitrogen. How physically big should I draw it if I were to go down in the periodic table, downward by one element below nitrogen? So if I were to go down one element in the periodic table, I would go down to phosphorus. Well, how would it be different? Well, it would have actually 15 protons in the nucleus, and it has a mass number on the average that's close to about 31. It's like 30.97. So a really common isotope must have 16 neutrons, which would weigh about 31. And if I were to jot some shells on here, first shell, second shell, and for phosphorus I got to go all the way third shell, I would have 2, I'd have 8, that's 10. And so, you could do 1s2, 2s2, 2p6. And then this outer shell here, if you check it, it would have 5. It would also be an s2p3 for a total of 5. So here is what I am trying to get at real quick on going down the periodic table. I hope that it makes sense to you that the 5 electrons in the outer shell of phosphorus, here's a term from the chapter, are going to be shielded or blocked from being attracted to the nucleus because they're way out in here, the nucleus is way down in here, and if you look at all of the negative charges in between there, it's going to be hard for the negatives in the 5 in the outer shell to get attracted to the nucleus. That's what electron shielding is. What that means is that phosphorus does not hold on to its electrons nearly as well as, say, nitrogen does, where they're closer. Now you say, well, why doesn't it hold on as well? There's more charge than there was. You're right, there are more pluses and there are more minuses in the atom, but here's the big thing. D is squared in the Coulomb law. That means if you go twice as far away, you only have 1/4 the force. So going out and having shielding where the levels are far out makes those outer electrons be held not much, very, very tightly at all. Now, having the extra shells and being held less tightly, as you go down a family on a periodic table, the trend is the radius gets bigger, and as that happens, that affects every single thing that's related to electrons and whether or not you want to gain them. You'll run across definition for electronegativity, electron affinity, and ionization energy. Get their definitions down because they're different things, but all of them are measures of electron love. How much does this thing want electrons? As you go down and the radius gets bigger, bigger, bigger with more shells, you continually get weaker on your electron love. All 3 of them, of those things. So that's a huge thing that ties a lot of stuff together. In just a second here, I'll wrap this up by talking about the weird part of this, which is what as you go across the period. Give me just a second. All right, so to wrap this up, I want to draw a couple more Bohr models, but I want to go I want to stay with nitrogen, so I'm going to clean this one off or move it or something. There we go. And instead of going down in the group, I don't want to do that. I want to go toward fluorine. So here's what, going this way in the periodic table, across the period, here's what fluorine would look like. It would have 9 protons in its nucleus. So that's more positive charge in the nucleus than we had. It has about a 19 mass, so there must be about 10 neutrons in the nucleus. Not in every isotope of this atom, but in the most common ones, because that's close to its average mass. Its shells would have 2 in the first shell, which would be like your 1s2. And then, of course, many of you know this from your blizzard bags and stuff, that there are 7 electrons in the outer shell. Now, here's what I want to say about this. Did I draw the size of it correctly? And I would submit to you that I should make a change that'll blow your mind. This orbit, I'm going to remove. I really ought to draw it more like this, closer and tighter in. And that would make a fluorine, even though it's bigger in atomic number, it would make it littler than an N atom. Just going across period 2, here's what I'm doing, picking a couple elements. Now, to understand why they get littler as you go across the period, For most students, going down, they get bigger, they let their electrons go easier, makes perfect sense. When you go across toward fluorine, you get to the biggest gainer on the whole table, and it's like, wonder why it's such a gainer. And here's my explanation. It's based on Coulomb's law. You have more charge in the nucleus, 9 protons, than you did before. It's pulling on 9 electrons total, but those electrons are all going into energy level number 2. They did not really go far out from where they were. Like, we're still filling the same level. As a result, Coulomb's law says that if you up the charge, more Q1, more Q2, more positive, more negative, but you don't stick them far away, there's going to be a greater force on them. If that's true, the outer levels of fluorine get pulled in tighter due to electrical forces than they do in things that are to its left, like oxygen or nitrogen or carbon. So the actual reason why fluorine is a monster gainer of electrons, really wants to fill that shell in, doesn't have nearly as much to do with the 8 in the shell as it does that if there's room in level 2 to keep filling them in, they don't have to go very far out to fit in the atom. And so the force just keeps building up and building up because there are lots of charges and they're still really close to the nucleus, to all that positive charge in that nucleus. And so the atoms actually, my picture that I have up there now, actually is more representative, even though it's a Bohr model, it's more representative of the size of how they're supposed to be. You will notice that if I were to go any place on the periodic table, doesn't have to be over here where I'm at, it could be over in the alkali metals. As I move toward the right, they're gonna get littler, and as I go down, they're gonna get bigger because you're adding a whole extra level and putting them out at a greater distance, and that weakens the force. That makes them have a low ionization energy. It's easy to get electrons away for the ones that have it hung way out there in space. So I hope that helps a little bit, because if you can understand why atoms get bigger as they go down and they get littler as you go across the period, every other trend will make sense.